So today, like we discussed in the last class, today we're going to talk about, we didn't discuss about the broadcast domain and collision domain and stuff. And we didn't talk about CSMA, CD, or, how those things are, utilized in Ethernet network. So, this is all again, when we say all this stuff, it's all about Ethernet, because Ethernet is the technology on which your LAN or your the system works, right? And what was the IEEE specification? It was, even if you don't remember, that's fine. IEEE 802.3, right? Okay, so broadcast domain and collision domain, let's say these are some devices connected over a shared media, yeah, and everybody can, let's say 1, 2, 3, they can, transmit their packets, they can broadcast anything over this media. So, let's understand it with respect to full duplex and half duplex also, because why this CSMA CD or collision domain on broadcast domain? What is the theory or a reason behind? And another one is full duplex. So half duplex is actually oldest thing. It used to happen when there used to be hub and stuff, but full duplex is today's technology. At switch level we all do is full duplex. So CSMA CD is, if you know, basically carrier sense multiple access, and later it came with collision detection. So basically, if somebody is transmitting, let's say this guy is transmitting data, at the same time, if this guy starts transmitting or any other guys start transmitting, because this is a shared media, a packet collision might happen. So how will they come to know if this collision happened? Because this is a shared media. So that is the point. That is wherein they introduced collision detection. Earlier it was not there. So anybody used to, transmit their data. They used to, there was a mechanism. We won't go into details because it's not needed. So there was a timer till what time they used to, wait for the collision domain packet. What used to happen if let's say if this guy transmitted some packet and this guy transmitted some packet, if there any collision happened, then what used to happen? There used to be a collision domain packet, you could say, or a collision packet rather. So when he is transmitting at only that time, until that time only, he can listen to those. He can listen to those collision packets, but then it's irrelevant for this guy if he stopped transmitting. So this is a old stuff. We are not gonna focus on that. I'll give you a real time scenario what we actually mean by half duplex and full duplex, and how we can actually say, how this collision domain used to happen in half duplex, and how it's not there in full duplex. So this, you can say, this is nothing but a highway, okay, and this is a one-way road. So vehicles are moving in this direction, yeah, in this direction, and this is a two-lane. So some vehicles are moving in this direction, and some vehicles are moving in this direction. So what I'm trying to say here is, this guy can transmit packet this side, and this guy can transmit packet this side over this medium at the same time. This is what happened in full duplex. You have different channels to basically transmit your traffic at the same time. So you don't have a collision domain. You don't. There is no problem of collision in this channel because you have separate lanes, right? To go this side there is a separate lane, to go this side there is a separate lane. But here it was basically half duplex is basically unidirectional, but it could be unidirectional at a time basically. So doesn't mean that this can only go in this direction, this can go in this direction, but to go in this direction, this communication has to stop. So that is where the problem was. That is where the collision used to happen. So again, like I said, we are not going to talk very much in detail because it's irrelevant in today's time. So this is what used to happen. Let's say these guys are going there and some guy come from this side, then the collision is going to happen. So for that, they came up with this collision detection, and then how it used to work in the backend, we don't need to know. It's irrelevant. So this is what happens. So this is half duplex. Is basically a good example is your walkie-talkie, right? Where your walkie-talkie is nothing but a half duplex example. One guy, speaking at a time, another can receive the traffic, and then he presses the button, and then the other guy can listen. But here we actually can communicate both ways at the same time. I mean, it's like while we are talking, or we are talking on the phone, right? So that is what full duplex or half duplex is, and that is where, I mean, this used to happen when we had full duplex, or or simplex. I mean, at the time of, there was another thing. I mean, there was another transmission mechanism. So basically, if I talk about very high level or about the transmission mechanism of the data, there were three types of transmission. One was simplex, another was, I mean, half duplex, yeah, and another was full duplex. So in simplex, what used to happen, it's basically one direction. So I mean, some of you are part of the Telegram channel, right? So that is that you can understand as a simplex. I mean, only I can put in message in that group. You guys cannot, send messages. So that is kind of a simplex thing. I mean, I'm broadcasting. You guys are getting the messages, or the message or the data, but you cannot transmit. But in half duplex, I mean, it's one at a time, but both parties can, transmit their data. And full duplex, like I said, this is the example of full duplex. So this is pretty straightforward. Yeah. So in today's scenario, we use half duplex switches. It doesn't mean that switches doesn't support. I mean, while you configure the switches, you will you will see this configuration available for half duplex as well. But I mean, you don't do it, right? If you do it, there would be a problems. I mean, you will see a lot of error messages or packet drops and etc. So this is pretty straightforward. I think there should not be any, confusion in this. And broadcast domain. Now let's talk about the broadcast domain, or like I said, I mean, let's say this is the topology where over a shared medium, devices are connected. So let's say this guy is sending its data. It will be broadcasted to all the devices in this network. Yeah. So this is basically the broadcast domain of this particular device. So basically, how many devices are there? 1 2 3 4 5 devices. So there could be there could be, I mean, depends on the number of devices which are connected over the medium. So I mean, here n is your 5, so there would be total 5 broadcast domains, right? Because this guy can also broadcast. I mean, everybody can broadcast over this channel, right? So that is how the broadcast domain is. And similarly, the collision domain, this guy can transmit, this guy can transmit, this guy can transmit, anybody can transmit. So there could be n number of collisions. So considering that, the collision domain will also be 5. I mean, it's not very tricky or difficult. I mean, it's also a pretty straightforward definition. Group of devices receiving broadcast frame initiating from any device within that group, right? So that could be, we'll see in a bigger topology wherein we connect routers or switches or PCs. Then we'll see how routers breaks the broadcast domain, or how switch, what happens when we add a switch. So we'll come to know about that, how these devices differentiate or break it up. Collision, again, the same thing. When two nodes are sending simultaneously over the Ethernet, they meet over the physical media, and there could be a collision. And again, like I said, what used to happen in collision domain, we'll come to know that what happens in the switches, what happens over the routers. And it's clearly says collisions are not propagated by switch routers or bridges. We'll talk about that. So let's say, let me draw one diagram and let me explain it to you. So let's say this is a router and connected to a switch. Again, let's say this is another switch. There are a few nodes or PCs or host, you can call whatever you want. These guys can, broadcast. And then here there is another switch connected to this switch. And let's say a few nodes are connected here. Likewise, and let's say another switch. So now talk about broadcast domain. I mean, what switch does, basically, if this guy starts broadcasting, it will reach to the switch. What switch does, when we'll talk about more about the switch, I'll again repeat this. But then switch will forward your frames to all the ports. Yeah. So basically, this is a one broadcast domain, but it also reaches to the router. But what router does, it actually breaks your broadcast domain. Router never forwards broadcast packets further. Yeah, router never forwards broadcast packets further. But when we will talk about DSCP, there would be something that you will come to know, that at that time you will realize that router is actually doing something else. So this is one broadcast domain. Yeah. How about the collision domain? So let's say this is a switch with 24 ports. Okay, this is a 24 port switch. So each port of the switch is actually one collision domain. Okay, so the number of this is just this would be a separate collision domain. This would be a separate collision domain. So it's actually breaking up the collision domains. Okay, and if this was not the scenario, I mean, from collision domains perspective, this is fine. Again, from broadcast, this was again a switch, right? Switch router. Now let's talk in this scenario. Here, this is a one broadcast domain. The entire, because switches can forward further your broadcast packet. From switch, it again reaches the switch and then it reaches the node. Here it reaches the node. Here from switch to switch, it comes to switch and then it comes to node. Because switches can forward, right? So whatever the broadcast one device is doing, ultimately what will happen, switch will forward to all. I mean, when we'll talk about how a switch functions, then again we'll repeat it. But then switch forwards through all its ports. So again, it reaches another switch and then the host. But whatever the destination MAC address or whatever the destination is, that guy will respond, and the rest of the nodes will discard it. That's a later part. But this is one broadcast domain. Okay. Another example, let's say this was the topology which we were discussing earlier, right? Let's say these are the devices which were connected here. And what we said, like if 5 are the devices, then broadcast domain are also 5 and collision domains are also 5, right? If we put a switch here, then this is a different collision domain, right? And this is a different collision domain, because this switch is breaking up the collision domains. But broadcast domain, it's a common broadcast domain, right? Switch can forward your packets to these devices as well. I mean, is it okay? Any confusion in this, in the broadcast domain or collision domain, guys? Or anyone?
It's fine.
Any confusion? Any question?
No, it's fine.
All right. I mean, you can ask questions if you have any doubt. So I mean, like I said, I mean, every port of a switch or a router is a collision domain. Okay, let me tell you another example. I mean, when we say, let's say these are the PCs, right? These are the PCs which are connected to a network. So these are the PCs. When I'm saying PCs, basically basically network, basically a NIC card, right? I mean, if it's a PC, it's a router, it's a network, right? So I mean, a PC can also be having multiple NIC cards, right? PC can have 2, 3, 4, 5 NIC cards also, depending on how many slots you have. So a PC can be part of multiple broadcast or collision domains in that sense. I mean, let's say if this PC is also again connected here. Let's say there is another NIC card which this PC has, and then there is another network where it is connected. Yeah. Then at this side, this is a separate collision domain and broadcast domain for this PC. And for this, to be specific, not the PC, but for the NIC card, because PC is nothing but, I mean, we are talking from the network perspective, right? So this is a separate collision domain or broadcast domain for this particular PC or end host. So a PC can have multiple NICs, right? So to be, I mean, like I said earlier, I mean, to be more precise, not the PC, but the NIC card, the number of networks a device or a PC is connected to, that many numbers of collision domains or broadcast domain it can be a part of. Okay, so that's your broadcast domain and collision domain, pretty straightforward. Okay, and I think we discussed about a physical layer, Ethernet also we talked about, right? This 10 base 2, 10 base 5, this is again cabling. When we'll talk about cabling, I'll tell you this again. I mean, what is 10 base 2 or 10 base 5? You can also check on Google. I mean, these are starting from the beginning. What are the types of cables which are available? But when we'll talk about color coding and cabling, I'll tell you this. Devices used at layer 1, or I mean, all the devices are basically in the same collision domain at same broadcast domain. So there is no hubs and collision domains. Again, we can talk, but this is irrelevant. Hubs no more are used. I mean, like I said, more end station means more collision. So in half duplex, hubs used to have half duplex. That is the reason there used to be CSMSCD. So not in today's time. Okay, layer 2 MAC address. I mean, we talked about this. Again, we'll talk again about this frame, Ethernet frame, but let's even talk about. I mean, there are different fields. This is your destination MAC. This is your source MAC. Length, you don't need to bother about it at the moment. Data is actually the real data, and FCSM preamble we'll talk later. Okay, so this is, I mean, there is nothing very fancy at the moment. Let's cover. Now, I think switches, I mean, from switch perspective, I already have told you that switch, each segment, again, its own collision domain, and broadcast are forwarded to all the segments. So basically, each, I mean, every port is a separate collision domain, and again, switch forwards broadcast packets. So it's, it can be a, I mean, what can be the scenario for a broadcast domain when it comes to a switch. Okay, we will not talk about this header at this moment. We'll talk about it when we'll do packet capture. I mean, on a higher level, this is the packet of IP packet. Let me show you that one as well. I mean, this is so what is layer? I mean, we know, right, from OSI model, we know, right, what are the layers which were there. First one was application, and then your presentation, then session, transport, network, physical, and then what, guys?
Data link layer.
Data link layer, and then physical.
Physical.
Yeah. So I mean, on layer 3, yeah. So I mean, this is you can say what basically it is about the IP. We are gonna talk about IP at this level. We're gonna talk about IP in detail, addressing and header and everything. So I mean, don't look at this. So physical layer, a data link layer, and the network. What used to happen at this layer? I mean, you don't need to check into. I mean, this is signaling and stuff. But then Ethernet comes, and then 80.23. This is MAC, and this is LLC basically. And now we have come to the network layer, the IP part. So we'll come. What is this network layer packet? I mean, at the moment, I also told you that in the earlier class that each and every layer inserts its own header in front of packet, and again we'll see it more in detail during packet captures. But from a layer 3 perspective, this is the IP header which I have. Let's say this is my actual, let's say for you to make it easier, and there is a router in between. This is A, this is B. Let's say 10.10.1.1. This is, let's say, .10. This is 20.1.1.1, and this is 20.10. Okay. So this guy want to talk to this guy. Let's say this is the IP header. We'll talk based on the IP header what information would be here, and then your source IP. So what is your source IP? 10.1.1.1, and then source MAC would be here, and then the destination IP. But we are talking about the IP layer at the moment, so they are not. It is not shown here, your MAC address and stuff. So the destination IP, and then the actual data. Okay, so this is what on a high level your packet looks like. What happens at this layer? The route determination actually happens. You will come to know about the route, that what is the best route to reach to this particular destination. In this topology, it's sort of just one hop. But I mean, when we talk about the bigger topologies wherein there are multiple hops, multiple routes available to reach here, then in those scenarios, this will tell you the route, which route you should take. And the network layer basically there would be a classification, that what kind of address class you belong to. So that is all we're gonna see. Okay, and so I think we can talk about IP addressing now, or I think we should talk about TCP IP model first, and then we'll talk about the IP addressing. Yeah. So I mean, we discussed how it is coming from physical to data link to to IP layer, and then the transport. What it says is basically upper layer applications. I mean, what particular transport medium I'm going to use, whether I'm going to use TCP or UDP. If you recall our OSI model, this is what we discussed, right? That what would be the medium of transport. Yeah. So I mean, it's like I mean, who is your carrier basically? Yeah. What would be the medium? So that is what comes at this layer. I mean, and then this connects your end-to-end applications. We'll talk about how this functions, and there would be something called flow control basically. We'll talk about in that windowing flow control, how it happens. So that happens. So that happens at this layer, and this is what we're going to talk more during your CCNA training. I mean, physical layer, I mean data link layer, and your IP layer and transport layer. I mean layer 1 to layer 4 basically. We will come to know. I mean, the application part comes a little later, but for a beginner or a CCNA level, or even if you're learning different technologies, so layer 3, layer 4 are the ones on which you're going to focus more at the moment. But when you talk about the applications, of course, we're going to talk that what are the applications that comes on layer 5 to layer 7, or application layer of TCP IP model. So we're going to talk about it. Okay, we'll talk about this, how the IP address is formed, what is the structure, what are the source bit or host bits. We'll talk about when we'll talk about subnetting. We'll talk about the IP header structure. So because we have talked about OSI model, so I think let's talk about TCP IP model. So I mean, this is just a theory that how it came into existence, though there was OSI model earlier available universally, but then how this TCP IP came in, then US DoD, Department of Defense, came up with this. And this is basically the reference model, and the application, the true application or the real-time application of that is TCP IP. That's what we discussed, right? So let's talk about, let's do some comparison, and then you'll understand it better. We discussed a bit earlier in the previous class. So this is again the naming. You are not gonna never talk. I mean, from a technical lingo perspective, you will never say internet layer. It always goes like, I mean, you will always say physical layer or data link layer or network layer or transport, and then here you will always say application. So that is how people communicate. I mean, they never say internet layer. Everybody will say layer 3 or network layer. Yeah. So I mean, during our, during your practicals or classes, or even when you are working, this is the terminology what you want to use. Internet layer. I mean, you will never say internet layer. It's always network layer. So yeah, this is the generic difference in terms of here it used to be 7 layers earlier, and here there are only 5 layers. The upper 3 layers are basically application, right? That is what we discussed, that this is the end application from where you are giving your inputs, and then it is actually putting it in a presentable format, and this guy is actually then initiating the session. Channel is getting opened up. So this is again a part of, I mean, when you open up a browser, access something, this all these things happen through your browser. So that's one of the example. Now talking about somebody who was asking in the previous class that let's talk about, I think that guy is let's talk about what are the applications, because people know about the OSI or the TCP IP, but then they tend to uh, forget or don't remember or don't understand that. One second, guys. That what comes at what layer, what application or what service which you will see on a daily basis. Uh, People don't understand that TCP comes at which layer. So I mean, if you know and understand, then it's easier. So these are the, you can yeah, somebody's asking something. Okay. So these are basically your applications, which comes at your layer 5, or you can say the application layer of OSI model. So, I mean, TFTP, file transfer, SMTP, telnet, remote logging, SNMP, will come to know what is SNMP, and DNS. Basically, this again, it's here, it's with respect to the router, that these are used by router, but I mean, these are used everywhere. Okay. So these are the applications which comes at this layer. Now let's talk about uh, transport layer, the mediums basically. So there are two mediums in general. One is TCP, as we discussed earlier, and another one is UDP. And here it says connection oriented, and here it says connectionless. So there is a difference between connectionless and connection oriented. We'll talk about it. That, I mean, when it says, so it's basically oriented means it actually confirms whether the channel is established or not, and how it happens. We'll talk about it. And UDP, it's not reliable. That is the reason it is also known as a connectionless. So this communication between us, when I'm speaking or you are seeing my video, this usually actually happens over UDP, because TCP is kind of connection oriented. I mean, it is not kind of, it actually connection oriented. So there are a few packet actions that happens between them to establish and secure, to basically guarantee the channel is established and two guys are talking and there is no packet loss between them. But in UDP, data transfer is the priority rather than the assurance that you actually are connected to me or I'm connected to you or not. So video and call cannot run over that kind of channel, because it will then would be, I mean, there would be a delay in the real time communication. So we'll talk about it. Okay. That how TCP works or how UDP works. So this is a TCP header, TCP packet. You can, if you want, you can take a snapshot. I mean, you can also see this is, I mean, if you know this, this is good. I mean, you should know this, but there are certain fields like if you don't know this, there is no problem. You don't know this, no problem. Header length, you'll see acknowledgement number. Of course, you will know when we talk about the sequence number again. Checksum, I mean, it's a common thing amongst all. This is urgent. Is there are different kind of flags in TCP packets. Every flag tells you about a situation, that what is the scenario. So we'll talk about, or maybe you can google yourself that what are the TCP flags, but again we will talk about it. And then these are the source port and the destination port, and this is actually your data. Yeah. And option, you don't need to, I mean, if you know, then fine. If you don't know, doesn't bother. And window is basically the window size. When we talk about the windowing, that on how many number of bits you're gonna use in that window. So that is, we'll talk about. I mean, this is a general. So I mean, on your level, I mean, if you know the header and the packets, it's pretty good. I mean, that is where you have the better understanding. So you should know this. But when we will do packet capture, then I'll again explain you in detail. But again, this is source destination port sequence acknowledgement. We'll talk about very soon when we discuss TCP three-way handshake and all. So yeah, that's it. I mean, if you want to take a snapshot. Otherwise, you can, I mean, I hope you guys remember this segment, right? Because in OSI model, we talked about different PDUs. Somebody never does anyone remember what was the full form of PDU or what is a PDU? No? Nobody remembers?
Protocol data unit.
Correct. Protocol data unit. So at each layer, it's a different thing. I mean, at physical layer, it's signal. At data link layer, it's frame, and then I'm not gonna repeat. We discussed in the previous class. So port numbers again. These are the common port numbers. You're gonna remember that FTP is a TCP. What I mean, you can Google and you can remember. I'm not gonna. There are 121024. These are known as standard ports, and these are actually, you can say reserved port by the authority or the body INA or INA for basically these services, FTP, Telnet, or whatever these services for these. And the ports after that are non-standard ports. So, but there are again in this range also there are certain ports which are reserved for certain things. So you can Google yourself, but you should know. I mean FTP, Telnet, SSH, or these things. When you do the configuration at that time, you will see that what are the services and what are the ports. So these are the port numbers. Yeah.
So what is RIP?
We'll talk about it. Who is asking? Hello?
Hello?
Salim, you are asking?
Yes, sir, I was asking about what is
I will talk about
RIP.
it's a routing protocol. It's a routing protocol.
Okay, sir.
It's not very used. But we'll talk about
Okay,
it.
sir.
We'll talk about the dynamic routing
Okay,
protocol. We'll talk about the RIP also as well.
Okay, sir, sure.
So TCP port numbers, and I mean this is again when we say port numbers, basically it is what we are talking about the transport. Yeah. So whenever we are going to communicate, when this PC is going to communicate with this PC, this channel or this communication, let's say this is 10.1.1, this is IP, though we haven't talked about the IP and its structure, but I think everybody understands this address. And let's say this is listening on 23. Yeah, and I mean, let's say this is 20 dot, let's say 10.10.1.1.11, and these guys are communicating with each other. So let's say this guy is trying to telnet, and then what is the port number of telnet? It's 23. So how this packet is gonna be for this guy? This destination would be, let's say, from Z to A. What would be Z address? It's .11, and then A 10.1.1.10, right? But then this is the IP. Then we are talking about the service. So the destination port is 23. If I talk about the packet, what is the source IP? 10.1.1.11. What is the source port number? This would be some random port actually. We'll talk about it. Some random packet. Some random port from this range actually. Most probably in some 55,000 series. And then what is your destination IP? This is the IP. And then the destination port is 23. So that is how on a higher on high level, this is how your packet will look like. Okay. So these are the port numbers are nothing but your basically services on which you are accessing something, or that service is running on that particular port. So somebody can, can access, or you are listening on that. So we'll talk about, I mean, you'll understand better when we do the practicals. Okay, TCP port numbers. Again, let's say another example. This is a server. There are two guys, 1.1.1, 1.1.2, and this is 1.1.3. And this guy is trying to destination port is 23. So basically, what we learned is 23 is telnet. So this guy is trying to telnet. So connection 1, basically from here, the source port, some random port to 20,000, sorry 2,000, and from here some 2,000, but the destination port is 23. So it's basically the IP is same, right? For this guy, 1.1.1.3, yeah. But then there are multiple machines or endpoints or clients who might be accessing this server. So how is that possible? I mean, at a time, let's say one guy is talking to one guy over one IP, but then do you think the same guy can talk to, I mean, a different guy can talk to this guy on the same IP? It actually happens because this never happens like IP, only on the basis of IP. It's basically layer 3 plus layer 4. It's basically IP plus service. Yeah. So I mean the combination of source IP service and destination IP service. Okay. So in this scenario, though multiple people are telnetting, this is also telnetting to him, this is also telnetting on the server, but then the destination ports would be, I mean, this combination will always be different. This combination, source IP plus source port and destination IP plus destination port. So that is how, you know, multiple people can communicate with the same guy on the same service. We'll see. I think there shouldn't be any confusion in this. I mean, this is not very, difficult. But anyways, any question until now? Any confusion? If you feel like something is not striking your head. Okay. All right. TCP three-way handshake, or when we talked about TCP, what we said is connection oriented, right? So what the connection oriented means, it means it's a guarantee. The packet from this A to B, from A to B will 100% reach here. So I have this reliability, connection oriented guarantee, or you can say the reliability. I mean, I need a reliability that packet is actually reaching here. Okay. It's not like that, like UDP, that there is no reliability. My data get lost. Or how would I come to know that actually whatever I sent has reached to this guy? So, I mean, before actually the data, before actual data transmission in TCP, what happens is they actually do exchange of packets. What we call is TCP three-way handshake or open connection to basically establish a session. So let's say if I want to send you something, I want to make sure that I am connected to you. There is a reliability. I mean, then there are additional things which we'll talk about later. But then there is a there is a confirmation that we have this channel. Now the channel is formed. Now we can do the data transfer. But in UDP, there is no reliability. I don't know whether the channel has been established or not. I am just sending the data. If you're receiving it, fine. Not receiving it, fine. I don't bother. But in TCP, it's not like that. So the communication or wherein you need the reliability of data transfer to be, 100%, or it should be, in those scenarios, the TCP comes in to play. I mean, TCP is basically, I mean, where you need your data transfer to be 100%. Basically, you want that your data should not be, I mean, you know that whatever I sent has received to the receiver. So what happened? I mean, we talked about flags in TCP. So here, what you are seeing is one of the flag. So let's talk about two flags at the moment, TCP flags. One is SYN. SYN is nothing but synchronized. Okay, and ACK is nothing but acknowledgement. Okay, so what happens in TCP? Host A, it sends a flag. It sends a SYN flag. When A is trying to communicate to B, to initiate the channel or to initiate the session, the first flag which TCP sends is SYN. So when we will do a packet capture in a TCP packet, you will not see the data transfer immediately. What you will see first of all is TCP three-way handshake. And the very first packet, what you see is a packet with a SYN flag. So what happens? You remember when we were seeing here this header. What happens is, what it does actually, it will change this to SYN. So when this will reach to your, I mean, then there would be other things. I mean, these all things works in combination. Okay. So when it reaches to your destination, it will see, okay, it's a SYN. So it's a session initiation request from somebody. So let's say that session initiation request come from A to B. Then we understand, okay, this guy is trying to, establish a session with me. Okay, I have SYN. So what I'm gonna do, I mean, then there would be the sequence number and stuff we'll talk again later. So this guy says, okay, I have received your SYN. And what he will do is, he will send a SYN. Okay, let's synchronize basically. So it's like you said hello, and then I said hello, but then this is my hello and this is your hello. But maybe my hello reached to you, but you are the one who said hello first. So I need to acknowledge that I'm saying hello, but I'm also acknowledging that I have received your hello as well. So I'm going to send an acknowledgement of this hello. So what it does is basically it sends a SYN plus ACK. So two things. It's SYN and then an acknowledgement. And then this guy, so this was SYN here, and then this guy sends a acknowledgement, not the SYN. Acknowledgement of its SYN that I have received your hello. So now that trust has been established. You see, send SYN, ACK, and then when I receive the ACK, okay, it's established. After this, the actual data is transferred. Okay, so let's say this guy is trying to SSH, which runs on port. Does anybody know? 22, 23, or 21? Which one it is? SSH.
So 22.
22. Yeah. So let's say he's trying to SSH this guy. So what will happen? A will send a SYN packet first, okay, to B. Let's say this is 1.1.1.1 and this is 1.1.2. And then B will send a SYN and then acknowledgement to this SYN, and then this guy will send the acknowledgement, okay, session has been established. Now I'll send the actual data. That data is basically nothing but let's say what was the IP of destination? 1.1.1.2, the destination service 22, which is SSH, and the source IP is 1.1.1.1, and there will be some random port. So this would be the IP header, right? We talked about the layer 3. This would be the IP header, but then there would be again data. I mean, you have done the SSH, then what you are doing further. So that would be here in your data, and then the other fields are for different things. So basically, this is the idea. Yeah. So basically, what TCP three-way handshake is that I'm going to talk to you, then this would be a reliable connection. You will make sure that each and every single bit reaches to you, you acknowledge it, and a secure and reliable data transfer basically. So, but in UDP, you want, this never happens because it's connectionless. So there is no connection confirmation. So I mean, this is a straightforward CCNA level interview question, you could say, that what is a TCP three-way handshake? You see, I mean, this is again a reset and fin. We're gonna not talk about it. Okay, here it is. From binary perspective, when you see the packet or the header, then see, I mean, because we haven't talked about at the end of the day, everything for a system or for a machine, for computer router, it's bits and bytes. So how does it come to know that which particular, header is a fin flag, or which one is a, SYN or ACK? So let me show you again that TCP. Where is the flag? Okay, here it is. Yeah. So you see, this is the field for flags. Okay, and here these are the flags in TCP packet. You see here, you see urgent, acknowledgement, post, reset, send, fin. Okay, so these are, I mean, when you see this, I mean, you will understand that at which place the unit is 1 and at which place it's 0 on that basis. So when we basically, when we talk about IP subnetting, at that time you will understand this better. So maybe I'll repeat it again. But then these are some of the flags, but you don't need to know that what Argent is doing at the moment. I mean, if you don't know about the TCP IP more in detail, this doesn't make any sense. And what is reset, all those things, I mean, and you're basically push and all. But I mean, I told you like 3 flags: SYN, FIN, and ACK. Okay, so yeah, so this is, you see, this is TCP session tear down or 4-way handshake, which I just told you. A FIN comes from here, and then the acknowledgement come here, and then this guy sends the FIN. Yeah, okay, I have this is what we talked, right? This guy sent the FIN. Okay, I have received your FIN. Here is the acknowledgement. Now I am uh, finishing the connection from my end, and this guy terminates. This guy sends the acknowledgement. Okay, final. And that is how you terminate. I mean, that is how the session teardown happens, or the gracious termination. I mean, why I said is gracious termination, because I mean, this is, yes, I mean, both are agreeing, but in some places there would be stuff where you will see that this actually is not aggressive. That is where the reset flag comes in, that it actually, I mean, something happened and this guy reset the connection. Basically, it terminated the previous session and it did a reset. So that is where your RST or reset will come in play, and we will talk about it. So that is another, let's say, for you, force flag to understand that this is what reset is. So you should know this, yeah, that how, what is TCP 3-way handshake or what is TCP 4-way handshake. These are I would say from interview perspective, these are kind of, you can say, straightforward CCNA level question. But again, I'm not I mean, we are not talking about questions or interview questions. We are learning it from doing, I mean, from technology perspective. That is what you will understand when you will do the labs or when you will work on the real time. So what session established or how it gets terminated. Okay, so I think this should be fine. Yeah, any questions? Okay, windowing. Okay, window size basically. So let's say this is A host, this is B. So what happens in windowing? I mean, as the name clearly suggests, basically the quantity of data, basically the quantity of data segment, right? Because we are at layer, or I mean, or layer 3, layer 4, you would say. So I mean, we measure it in byte, right? How many number of bytes can be sent in a single window? Yeah. So that is what windowing is. I mean, let's say, for example, let's say here the window size is, I mean, all these things, the all these things are this negotiation and channel. These everything, these are, these are discussed, or you can say negotiated during that 3-way handshake. I mean, because you saw, I mean, in the IP header there was a window field, right? So what is my window size? When I say SYN, there would be details about other fields as well. So this guy will come to know that what is my window size and all. So that is where the initial negotiation in terms of, you can say, how we're gonna deal with each other, that will happen in those, in that TCP 3-way handshake. Okay, so let's say here the window size is 3. So for example, 3 means, let's say, 3 packets. So I mean, let's say this TCP SYN SYN and ACK, and then ACK, this has happened. Now the real data transfer is going to happen. So let's say this guy sends a first packet, okay, with some sequence number. Of course, there would be a sequence number. Otherwise, how will this guy come to know that this is the first, this is the second, this is the third? So let's say the sequence number is 1, and and then this guy sent another packet, 2 and 3. Okay, because the window size was 3. Okay, so now what I mean, then again, what happens is there are mechanism wherein, I mean, if the window size is 3, let's say this guy has received 1, 2, 3, then he will send an acknowledgement. Okay, that I have received 3. Okay, I have received 3. The acknowledgement for 3 will come, or maybe let me show you the other image which already is there to understand this better. Yeah, so let's say 1 I have received, send 2. So basically I have received the acknowledgement. Okay, this is about the acknowledgement, not the windowing. But what I'm trying to say is there are various mechanisms. Let's say 1, 2, 3. After TCP 3-way handshake, the data transfer happened, and I have received 1, 2, 3. So what I'm gonna do is I'm gonna send an acknowledgement with a sequence number that this is what I have received. Okay, so this guy will come to know, okay, till now, till packet number 3 he has received. Now I have to send 4, 5, 6. Yeah, and then this guy will again send the acknowledgement, this is what I have received. There might be a scenario wherein, let's say I have received 1, 3, but I did not receive 2. So what I'm gonna do is I'm gonna send an acknowledgement that I have received. How that happens, we'll talk in detail. That I have received, for example, 3, 1 and 3, but I haven't received 2. So there would be a retransmission request of 2. So this guy will again then retransmit 2, and then let's say 4, 5. So let's say I have received 2, 4, 5, and then the sequencing is happening here because earlier I did not receive 2. So when I received 2, then what I did sequencing of the packet. I mean, that those all things are part of that flag and how this whole sequencing and everything happens. But now at the moment, what we are understanding is the window size. So this is basically what is the chunk of data what we can send in a single go to the other side, and then how other side basically acknowledges it, and how it determines that how the sender come to know that what he has received or what he hasn't has received. So that is what windowing is. I mean, whatever the number of bytes you are sending in a single go, and then again the packet and all is from nitty-gritty perspective, that how that acknowledgement and sequence comes in picture. So this is again here, again they are talking about TCP simple acknowledgement, like you send 1, I received 1, I send, and so basically one more thing. So let's say my sequence number of packet 1 was, let's say I sent a packet with a sequence number 1. So what it does, it basically it actually increments that acknowledgement number with that sequence, that this is what I have received. Yeah, so send 2, you see, send acknowledge 2. Okay, received acknowledge 2. Then what it will do, send packet 2, then 2 plus 1 acknowledgement 3, I received 3, then 3, then 3 plus 1. But here the window size is 1 packet at a one time. But what is happening, the acknowledge which I am getting is 1 plus 1 basically. That let's say you have sent some packet number 50,000 or 55,000, then the acknowledgement for this would be 55,001. Okay, but let's say if it was like 1, 2, 3, 4, 5, then the acknowledgement, let's say 5, then the acknowledgement would be, let's say 55,005. Okay, so this is how the acknowledgement is basically one additional to that this is what I have received. And then, like I said, there would be scenarios wherein, let's say somebody sent 5 packets, but only 4 were received. A particular packet lost during the transmission somewhere in the path. So you then send a request, that you send an acknowledgement that I did not receive it. So there would be actually a retransmission request for that. Okay, and then that guy will retransmit it. So that is again this TCP IP I mean, TCP/IP. When I say TCP/IP, it's a protocol suite. Okay, because IP and there are multiple things in TCP. But this is, I mean, on a broader level, how the packet exchange on a higher level happens in a TCP channel between two hosts. Okay. Any questions? Again, I think I'm telling you in advance.
No, sir.
In all the slides, it's there. I mean, let's say again there is a sequence and acknowledgement number. What I told you. For example, this is my source and this is the destination, and this is the sequence number, and this is my acknowledgement number from my end. Let's say I just send number 11. Okay, and then I just got number 11. Now I need number 12. So I mean, this is how I send. And you see the acknowledgement packet, what is happening. I mean, don't think of these things. I mean, sequence 100, and that is fine. But then acknowledgement is getting incremented by 1. Then this guy is sending 11. Then how it is incremented by 1. So I mean, like how I told you earlier. I mean, this is how your sequence and acknowledgement basically works. I mean, this is just theory, but you will like it better when we will do the packet capture. Again, windowing, we already have discussed it. There can be multiple window size. I mean, one set to 1 or one set to 3, and then how when you configure one, then basically for every packet. So when you say what you do, I mean, when you set a window size to 1, for every packet there is an acknowledgement, right? You have configured window size of 1, the sending machine waits for acknowledgement for each data segment in transfer. But if you configure 3, it's allowed to transfer 3 data segments before an acknowledgement is received. So like 1, 2, 3, and then acknowledgement. 1, 2, 3, and then acknowledgement. But here, packet acknowledgement, packet acknowledgement, packet acknowledgement. So we keep a window size. I mean, this is how for the faster data transmission, or I mean, it depends on the media basically. So windowing, okay, again the same thing, yeah. An example of like how it is happening, with window size 1, or how it is happening for window size 3, yeah. Transport layer reliability. You see, this is how we talked about it. I mean, how it comes, how it is reliable, because for everything, whatever we are transferring or whatever we are sending across, or between two hosts or two machines, for everything there is a confirmation that what I have sent, what I have received, right? So let's say 3 packets, acknowledgement number 4, packet number 4, but packet number 5 connection got lost and something happened basically, and then we sent 6, and this guy sent an acknowledgement of 5. That 5 means that I did not receive this packet. Send 5, and then acknowledgement of 7, because now I received 1 to 6. So one acknowledgement was here, and then another final acknowledgement that I have received. So that is how it is reliable. Yeah. So that is why we say reliable. Our connection oriented is I established, okay, we are done. We said hello to each other. We know each other. Now let's do a data transfer. But in data transfer, if any packet get lost, because for every packet there is or for the data transfer there is a mechanism by which it comes to know that actually my data, what kind of data has been transferred, what's pending, what gets lost, what I need to do the retransmission. So that is the definition of reliable from TCP perspective. So that is where I mean your all secure connections where the data reliability is a must thing is TCP connection. So what we are talking, I mean the audio video is never a TCP, because you see why it's not TCP. Any example? I mean any answer if from your experience, if you know why it's not TCP. It should be TCP, not UDP. I mean, though we haven't talked about the UDP, but from your basic understanding, can anybody tell why it's not UDP or why it's not TCP for UDP?
Sir, it's
Because
TCP
receiver,
Go ahead.
sir, as it is maintaining a connection, that's why it is TCP, and in UDP we don't make a connection.
No,
as
that
it
is
is currency.
the definition. But I am asking you from real time perspective that let's say audio video, why it's not a TCP or why it's UDP?
TCP is like sending and receiving, and UDP is just receiving.
No. That is not the. I mean, UDP, in UDP also you do a data transfer. It's not like sending and receiving. In UDP, what I need is a faster communication, faster data transfer. I mean, do you think? I mean, let's say, I mean, during this audio video, if this is a TCP connection, then there would be, kind of delay, or if something gets lost, there would be a delay. And I mean, this is very quick. I mean, you immediately need my voice, immediately need my audio. Yeah, so I don't rely. I mean, there are other mechanisms for that reliability, or delivery of data, or packets, audio or video. But the example is audio or video has to be real time. I mean, you need to get it immediately. So I don't need any assurance that you are actually getting or not. But here, what is the priority? Is the faster delivery of data. But in TCP IP, I mean, it's not like the TCP is slower, but there is a reliability or guarantee that this needs to reach there. I mean, let's say if you don't hear something, you will say, I did not hear it, right? Let's say I'm speaking and you are not able to hear it. Immediately you can send a packet, I could not hear you. So then I'll do a retransmission for you. So in that sense, right? But then TCP is, I won't say that it's a machine to machine. I mean, it can be anything, but in voice or audio, if you are not hearing, let's say, if you are not able to hear me, you can say that I cannot hear you, right? Because this connection or this data transfer between two parties needs to be very fast. So that is where the UDP comes in, audio or video. There is no, I mean, if signal got lost or you did not receive one packet, that is fine. You can say that I did not receive a packet, right? So that is the reason. Faster, very fast communication, wherein I don't need any guarantee that you are getting 100% of the data, whatever I'm transmitting or not. So that is the example, not the definition. I mean, UDP also, I mean, this is the UDP connection between us, whatever I'm saying. And when you speak up, so you are also transmitting from your end. So that doesn't mean when you say that I don't need to transmit from my end. No, that is wrong. I mean, it's again, you are also sending something, I'm also sending something, right? But it's a faster communication. So for audio video, we need a faster communication rather than the guarantee that everything is reaching you or not. If not reaching, you are gonna send your transmission from that side saying, hey Deepak, I cannot hear you, right? So that is why UDP is used in you can say, or I mean, in audio or video. I mean, there are other things that will come to know that what are the other protocols in the background, but in general, I'm saying, okay. But again, I mean, those protocols or those services would be part of UDP suite, you can say, yeah. So, like for example, for TCP. We talked about, let's say, SSH or Telnet or all these things, then there would be certain things in UDP. Yeah. So you'll come to know when we talk about it. Or you can Google yourself that what are the protocols under TCP suite, or what are the protocols under UDP. So that is what I mean. If you know DNS and stuff, but DNS again is TCP and UDP both. We'll talk about it. So windowing, I mean, we talked about flow control. Okay, flow control is another, you can say, what it basically does is, overflow, or basically that you are not, sending continuously, and my buffer size is, so whenever I receive any data, let's say whenever there are, I mean, when these guys transmit and receive, there is a buffer size, there is a memory of this machine, right? There's a capacity that this is what I can store. Yeah, this much this much bytes of the data which I can store. I can do sequencing and all the operation on it, and then forward it further. So that is what we actually control in the flow control. Flow control is used to ensure networking devices don't send too much information to the destination. Overflowing, basically buffer overflow. So there is, I mean, if you guys know, just from this terminology, one new thing for you, there is something called as buffer overflow, actually, not buffer flow. buffer overflow attack. This is a kind of attack. Basically, somebody is sending too much data to you that you are not able to process it, and the destination got chopped. For example, I mean, that is how some hackers or some attackers, what they do, they will transmit so much of the data to you that a buffer would be overflow, and you won't be able to process, or you won't be able to cater other requests. So to make you down, this is a kind of attack what happens. So maybe you can Google yourself that what is buffer overflow attack. So that is and again, to ensure that basically your destination doesn't get overrun by too much of information. So I mean your CPU, would be consumed a lot. So you won't be able to handle it. I think it's there in the next slide. So you see, this is what you're sending, and if you are not, this guy is acknowledgement is this, but we don't talk about. I mean, you see, this is how, this is how they are talking about window size also. One more thing, we talked about window, but there is another capacity, there is another term which we called as sliding window. Okay, so let's say this you can say is the example of sliding window. Yeah, it's here only. So what happens, let's say initially you sent me something and I agreed on okay. I mean you set a window size from your end, let's say 3 or 5 or 15 or whatever. But then when it came to me, I said, okay, your packet says this is the window, but then I can tell you about my capacity. This is the space which I have opened for you. So this is basically, I mean, whatever the earlier window size, my CPU was busy, I was not able to process. But later, when the resources are available, I can say, dude, I have this much of window size available. You can send a lot of chunk, a bigger chunk of data. Yeah, so that is basically the smart mechanism of TCP/IP. That is where known as sliding window, or basically sliding window protocol, or sliding window. Yeah, that otherwise, I mean, I cannot be just like, I mean, whatever we have, let's say in the very first transmission, whatever the window size this guy has said, if I have the bigger capacity, then that would be underutilization of the resources. So that is also not good. So these are the mechanisms, or these are the properties of TCP, which makes it pretty amazing. That it's reliable. You get the guarantee, and how I can make it faster, or how can I make it slower, and the processing of everything. So there is a guarantee of everything. So there is no data, uh, any kind of data doesn't get lost in a TCP transmission. So those are the mechanisms. I mean, this is it's still not on a very high level, but yeah, on a generic level, this is how a TCP/IP works. But I mean, if you want to understand it very in detail, you can analyze what happens inside a TCP flag, in a TCP header, basically, not flag. Flag is a part of that header, and what are the different fields. But I mean, you don't need to go through each and every field in that header. What you should know is what is your service field, what is your flag field, what is your IP header field. So you basically know when you open up a packet, you basically know that this is the IP field, this is the service field, this is the flag where the flag is stored. Yeah, and at the end of the day, all that information then finally gets converted to bits and bytes, and the different position of bits. And then when it gets summarized, that I mean, for a summary, you feel okay, this is the number, but when it reaches the end machine, it actually defines the particular location of that bit. That if the bit is set to 1 on this particular location, that flag is getting changed to some different flag. Let's say it was seen on first position. Let's say it's 3. If it's 1 on third position, it's a different flag. So I mean, when we talk about subnetting, then you understand, okay, how, I mean, when we say this particular address is a class A or class B or class C or whatever, for a human, it's pretty easy. I mean, seeing, okay, this is this range, so this is class A or class B or whatever. But at the end of the day, how the machine understands? For machine, it's 0, 1. So where that 1 is placed, or where that 0 is placed in a particular sequence, that is how your router, or your any device will understand that what particular of class it is, or what particular flag it is. So you can go through TCP header. I mean, it's always good to know that those headers. I mean, especially for you guys because you are early in your career, and initially the more you learn about this stuff, the better it is. I mean, on a higher level, when you work on a higher, higher job roles, where you are working on not on very low level fixing things on device level when things are not working and then you are fixing it at that level, these things are pretty handy, and if the more you know, the easier it's for you. But on a very high level, even if you don't know, I mean 90% of the people who don't work at a tech level where they are working or every single day on a packet level, that doesn't matter to you, to them. I mean, yeah, that is how it is. I hope you got the point. But I mean, at your age or experience or your career phase, you must know this. Okay, UDP. Okay, guys, we'll take a 10-minute break and then we'll continue our class, or we'll do another 1 hour. We'll not do till 12 today. There is a festival in India today, so I'm not going to continue for 3 hours today. So I need to go somewhere, but we'll continue for another hour. Take a 5 minutes break or 5-10 minutes break. I'll put a timer on the screen and then we'll continue. Okay.
Sir, 10 minutes.
Yeah. Okay. 10 minutes. 10 minutes it is. All right. UDP. So basically, I mean, as you can see, UDP, it's connectionless, what we say. Because I mean, it's again, I mean, everything, what we talked is, I mean, it's over the IP, right? Whether it's TP, TCP, or UDP, it's over the IP stack or IP header or IP layer or the network layer. So it's basically connectionless. What it mean is, I mean, it's like I said earlier. I mean, this basically it doesn't bother about or doesn't involve the overheads of what TCP does. I mean, TCP what it does. I mean, error checking or or the reliability thing. I mean, or whatever you can say the failure, the point of failures. What can be there, what TCP checks. I mean, error checks, or what is the sort of retransmission of missing data and that kind of stuff. So basically, it's suitable for real time or high performance applications, and it basically doesn't don't require verification or correction basically. So basically, I mean, those verification or that correction that again can happen, at application level. I mean, you'll understand. So when I was saying to you about audio and video, right? So what we said is UDP is real time, and why we use UDP at audio video level, because it's real time. So we don't bother about the problems, but that verification or problems what can occur at the data level, that can be actually verified at application level. There are mechanisms, so you'll come to know about that later. So yeah, I mean, it's a simple protocol basically. Yeah, so there is no exchange or acknowledgement or guaranteed delivery like we discussed earlier, or error processing or retransmissions. So basically what we just said, what we just discussed. So that is, I mean, it's basically faster. So you see, TFTP or SNMP, these are faster communication. It doesn't need any sort of reliability or 100% data transfer or that kind of stuff. DSCP, DNS again. DNS is again both TCP. I mean, here it's a UDP. On a generic level, it's TCP. Yes, it is. Sorry, UDP. But DNS also uses UDP. You'll come to know, or maybe just to tell you right away. So basically, I mean, okay, let's talk about it very quickly about that. So when you access any website at your level, whatever the DNS query or resolution happens from an end machine to one DNS server, that is actually UDP. So DNS port number is 53. That is basically UDP 53. But what happens? Let's say I mean, I'm going very high level. Let's say you reach to your ISP DNS. I mean, your local DNS or your cache, whatever, doesn't have that name to IP resolution information. So it reaches to your ISP DNS, let's say, and that also doesn't have, that information. Then it goes to root, and then further server DNS servers in a hierarchy. So those DNS to DNS server communications, they are actually TCP communications. They are not UDP communications. So that is why DNS is TCP and UDP both. But at your level, it's UDP. At those levels, it's TCP. I mean, nobody actually, most of the people don't know that this also uses TCP. I mean, if you don't know the overall DNS, then you will always say that it's only UDP. Okay. So yeah, this is UDP segment format. There is nothing much as compared to TCP. It's very obvious. I mean, there is a source port, destination port, and data, right? There is no sequence or acknowledgement field. Nothing we are talking about here. I mean, there is no sequence, there is no flag field, nothing is there. Yeah. So so that is how, I mean, it's pretty pretty fast. It's simple, efficient, but not very reliable, like we said earlier. So that's what I mean. And the best example what I gave you earlier is this audio video transfer, what we are communicating through. Yeah. But again, that reliability, there are other mechanisms. Okay, TCP versus UDP, a quick comparison. It's sequenced, unsequenced. We talk about sequencing, and then we, sequence everything up. Reliable, unreliable. It's pretty, straightforward. Connection oriented, connectionless. This also, window and all, and virtual circuit and lower overhead. I mean, these again are, things like either jack or those controls and all. So that is what happens at, you could say, at code level or software level. But then there is, I mean, because it doesn't bother about these overheads. So low overhead, I mean, it's pretty straightforward. So these are pretty basic, differences between TCP and UDP. So yeah, so this is again, now we are, because we were talking about TCP UDP, now let's come to internet layer, or basically the network layer, or layer 3 of OSI. Okay, so IP is the is the main protocol of this layer. Okay, and it will basically, it's it is connectionless. I mean, it's not like TCP or UDP that you are forming any sort of connection. No, and it is the carrier. Yeah, it is the carrier who's gonna carry that. Okay, how this is the, or rather, how you can say carrier, or maybe how the route selection will happen. That is what is determined at this layer. And transport layer, what we determined is the medium, by which medium are we gonna transfer the data. So again, the examples are IP protocol at at a network layer. ICMP, we'll talk about what is ARP, we'll talk about it. What is reverse ARP, we will talk about it. Okay, so this is a generic overview of layer 3. Okay, and IP data. Okay, now there are many things. We're not going to talk much about it. TTL is called as TTL. Just we'll discuss. This is a very important thing in networking. You'll come to know about it. And then the version, basically, this version defines whether it's IPv4 or IPv6. Yeah. And then the header length, priority, and type of service. Again, we'll talk about this. I mean, these are something you don't know. It doesn't matter for you. What matters is these two fields. And again, this is pretty straightforward. And I mean, these are the two headers in general. What matters to you? Others are information which, if you don't know at the moment, doesn't matter. If you don't know even later, doesn't matter. But if you're working in that kind of situation or in that kind of role, and it's always useful. So yeah, and then this is data again. Whatever it is. So yeah, again, I will again saying it again. It's better to know. So at your personal level, when you are doing a self-study and stuff, I'll advise to go through headers of different services, ports, protocols, IP, TCP, UDP, and stuff. Protocol field, I mean, it's again, this is how this is the protocol field. When they say protocol field, it's actually determines your TCP, UDP, and then your IP. Yeah. So yeah, so this is, there is nothing fancy there. Okay, and yeah, internet ICMP. Okay, we'll talk about what is ICMP. This is pretty straightforward. We are not going to talk about it. We'll come to know that what are the different ports, what it use, how does it actually work, what is the idea behind it. Eco is what is ping and what is destination and ritual. When we'll do ping and all, we'll talk about the ICMP, how does it work, and what runs in the background, or how does it actually works. And there are certain services or protocols which actually uses ICMP. So we'll talk about them. Okay, ARP, address resolution. Okay, so this is again, for example, when you all know, right, DNS, what it does is, let's say you say abc.com, what it does, it gives you, on a very high level, it gives you the IP address of abc.com. For example, you open up your browser, you put in a URL abc.com, and then it goes to your local host and DNS and stuff. I mean, and then basically your machine comes to know, okay, this is the IP I need to get to. Okay, so similarly, what happens here is, in ARP, what happens? We'll talk again in detail. So this is basically IP to MAC binding. Not MAC binding. Not MAC binding. What should I say? IP to MAC and IP to MAC resolution. So that is what the name says. Address resolution protocol. Yeah. So when we talk about, I'll discuss this example. But again,
Is it MAC to IP or DNS to IP?
no. It's not DNS. Forget about DNS here. No, it's IP to MAC. DNS, I gave you just the example that how that DNS resolution happens at that level. So it's a similar resolution, but it's IP to MAC resolution. Okay. So for a quick example, let's say there are multiple machines, or maybe this is a switch, let's say, and there are multiple machines which are connected here. Though we haven't talked about ICMP and ping, but still I'm using ping or ICMP. Let's say this is 1.1.1. Let's say this is 1.1.2, and let's say this is 1.1.10. When we'll talk about switch again, this example is gonna come again. So let's say I want to say hello to 1.1.2. Okay, so what I'm gonna do is, okay, then what would be my packet at this level? At A want to talk to B. So basically, source IP is 1.1.1.1. Source MAC address is, let's say, x.x.x.x, and then what is my destination IP? 1.1.1.2, and what is my MAC address of B? I don't know at this moment. So let's say f.f.f.f. What happens? This packet reaches to here. I mean, basically, it does a ARP broadcast. Hey, who has this IP? So this broadcast gets forwarded to all the machines, all the ports of that switch, where whatever is connected on those ports, and it reaches here, it reaches to another machine. But the machine who is having this IP address is gonna respond back. It is gonna respond back that this is my IP, and hey, this is my MAC address. So then this guy will come to know, okay, this is the MAC address of B, and switch will also learn that these are the MAC addresses. This is the MAC address of A coming on. I mean, we'll talk about this again when we talk about how a switch works, the very first thing on a switch. And then, okay, then this will be updated here with the MAC address of B, and they will come to know, okay, this is the source MAC, this is the destination MAC, this is the source IP, this is the destination IP, and that is how he will be able to communicate with B. So we'll come to know when we'll see how a switch performs, the CAN table, MAC address table, those concepts. At that time, we'll see in detail that what actually I'm trying to say now. Reverse half, we are not going to talk about it at the moment. Ethernet, we have talked. What is Ethernet part of? I mean, it's LAN technology. Again, what is 10 base T and stuff? You can, when we'll talk about cabling, then I'll tell you this terminology. We are not going to talk about cable at the moment. Not even DCP IP math. Let's talk about TCP IP addresses, okay, or basically IP addresses. So let's talk about IP addressing, okay. Does anyone know what are the different classes of IP addresses? I mean, classes is just a classification, but I mean, it is classless at the end of the day, but again, there is a significance. So
Class A, Class B, Class D.
Class A to E.
yeah. Those are the things. Yeah. So okay. So okay, let's talk about IP addressing. So IP address, or how does it actually works, or what is the concept behind? So first thing is, it's you can see IP addressing. It's 32 bits. Okay. So there are 4 octets in which our IP address is defined. You see, there are 4 octets. So for example, let's say one IP is 10.1.1.1. So this is first octet, this is second octet, third octet, fourth octet, and total 32 bits. So one octet has 8 bit. Okay. So let's say first octet is 1, 2, 3, 4, 5, 6, 7, 8. Now octet number 2. Okay. Likewise octet 3, likewise octet 4. Okay. So this is what 4 octets, 32 bits, and each octet has 8 bits. Pretty easy. Now, how does an IP address, I mean, what are the components? So basically components is how a IP address forms. There are 2 things. IP address is nothing but network bits plus host bits. I was thinking that we'll do a lab today, but I think it's not going to happen today, maybe in next class. So network bits and host bits, what does it mean? So I mean, if you look at this diagram, it says network and host. These are host bits and these are network bits. And what is this classification again? Now one more thing. And now again, if we go one bit by bit, then this is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7, right? Now everything comes in 2 to the power, okay, 0 or 1. So this actually turns out to be 1, and 2 to the power 1 is 2, 2 to the power 3 is, sorry, 2 to the power 2 is 4, then 8, and then 16, then 32, then 64, and 128. And if you add up, it actually becomes 256. The entire, 255. Yeah, if you add, it will be 255. Okay, so the entire octet is the sum of all the bits. If they all are, I mean, we are not gonna say about that. It's 255. You see, so we'll come to know that. I mean, what is network and subnet when we'll do subnetting. But this is the idea. I mean, IP address is basically network bits plus host bits. Okay. Now there are 3 different classes. So class A, class B, D and E, research and multicast. So this research you will never see, but there are multi-class addresses which are defined in this range that you will see or use over a period when you will talk about different documents. So class A address is when the first octet or is your network bits, all the 8 bits. Okay, or rather, let me keep it this way. And the rest of the 24 bits are 8.8.8. I mean, not dot 8, but 8 bits, 8 bits, 8 bits. These are host bits. Okay. So this is what becomes your class A, and then the first two octets are, you know, host bits. Then it's your class B, and this is your class C. But when we will be, you know, talking about, or when we will be doing this real exercise, then you'll come to know that how we go from left to right to determine that what, I mean, when you will be defining or determining the subnets, at that time we will discuss that, you know, how many number of network bits would be there and how many number of host bits would be there. That calculation goes from left to right. You'll understand when we will do that calculation. Okay. So this is a generic classification. Now I'm going to show you that, you know, the ranges also. I mean, does anyone know the class A range and class B range, class C range? Anyone? No? What is the IP address range of class A, class B, class C? Nobody knows? No problem. Here it is.
I know.
Okay, great. Anyway, it's here already. So yeah. So class A is you know, from 1 to 126. So what does it mean? Let's say 8 bits, right? 8 bits were there, right? So let's say first place, second place, third place, fourth, fifth, sixth, seventh, and then eighth. So let's say all the bits are 0. Okay. I mean, there is no, and this is 1. Then what it gonna be? 1, right? And then there would be combinations, similar combinations like this. So, and when it becomes 1, and what it becomes? 126. When let's say the rest are 0, let's say, for example. I mean, I'm just saying, I mean, just for the sake of explanation. So you see, again, when we will do subnetting, then you will understand it in a better way. So 1 to 126 is the network bit for class A. Then 128 to 191 is class B. Okay. And then 192 to 223 is class C, and this is multicast group. We'll see when we do OSPF and stuff. Okay, so there is 127. Does somebody know what is this IP address? 127.0.0.1.
Loopback IP.
Loopback IP, or you can say localhost. Okay, so you can say loopback IP, but we'll talk about what is loopback. But if anything, maybe if any service, for example, in your, or you can see it in your laptop also. And what is localhost? I mean, you do your work. Maybe you can Google yourself, and then you'll come to know what is localhost. Okay, so these are the ranges. Again, I'm not getting into the details, just an example, but things would be much better when we talk about IP addressing. Now, host addresses. Okay. So network address is, I mean, what I said is an IP address is network bits plus host bits. So when my one octet defines the network address, that this is the particular network. For example, let's say 172.16. Let's say class B. Yeah, 172 falls somewhere between 128 to 191, right? So this would be a class B address, and rest of the, you know, bits in the host, not second octet. This would be the network, right? Because class B is basically first two octets, right? And then the remaining bits would be my host bits. So that is where that is how, you know, the host address will be defined. So when we say IP, one IP, actually IP address is basically, you can say, a host address, right? Because the first, or the, I mean, the network bits actually defines that this is the subnet, or this is the network you belong to, and then this is your exact, I mean, then placing all those host bits in places of host bits, that is how you get a specific host IP, right? So that is basically nothing but your host, host IP or host address. We'll talk about this later. This CIDR or classless, that you'll come to know that what is classless. But there is one thing which I'll quickly tell you. Well, there is one thing. One is private range of, because IPs, and one is public range of IP. Does anyone know what is the difference between private range of IP and public range of IPs?
So we can use private range to do testing, and public range are defined by only ISP.
What do you mean by testing?
Like, sir, if we have to connect a bridge to a virtual machine, or
So public
No,
IP
private.
is suppose if you are
The private.
configuring a network in LAN or something like that.
Okay. No problem.
Private IP is IP that you using for any network, that, but is not out. It's not go to out, but it's only for local network. But public is they go to internet to take some information for internet. That is probably because this is you go to internet, but between all of them you using for NAT. Then if you local network, you make you want to go to internet, you use NAT to translate that IP.
That is, I mean, that is again a further thing what you were saying, NAT and all, but that is right. I mean, that is right. So basically public IPs for you as of now, public IPs are basically IPs which are routable on the internet. Okay, which actually your internet understands. Okay, so there is a range of IP. I'll tell you, there is a subnet range, or I mean, again, this is a beginning because you don't even know at the moment what is subnetting and all, but there is a range of IP addresses which we call it as a private range of IP, where it defines that these are the IPs which you can use locally in your network. Okay, so for example, what I mean is, let's say this is one office. Okay, public IPs are the IPs which your service provider gives to you, on another definition you could say. I mean, because these are publicly available, yeah, and these are understood by internet, and these, they have a cost associated with them. I mean, you doesn't mean, for example, your mobile number or my mobile number are different. That is how we are communicating with each other, right? And you are calling on a specific number. Not two people in a public domain cannot have a same phone number, right? But I mean, people have a different name. I mean, people have same names, and in their locality or in their network, and when people communicate, I mean, basically, your name could be similar, but then those names cannot be. I mean, what should I say? I mean, publicly, I mean, if I'm addressing somebody, then there should be a distinction that this is your distinguished IP, for example. So I mean, you will understand, because I mean, these are again, these are assigned by your ISPs, or how you get them, or how internet works. We'll come to know about that. What I mean is, these range of IPs you use locally. So basically, let's say in your organization, or in your company, or you're at home, whatever your office network or enterprise network or home network, there is a range IP. There is a 10. I mean, I'll tell you what RFC it belongs. Again, then what is RFC? You will ask. We'll talk about this also. There is a range of IP which is used within an office, or within, at home office, or within your premise. Those are private range of IPs, but they are not routable or internet. What I mean is, let's say your address is 10.10.10.10. Internet does not understand 10.10. So we'll talk about that. Who defined this structure? We'll talk about it, and then why these are not routable. And two, So let's say when your address is 10.10.10, and or let's say your home router is 192.168.1.1 or 1.10 or whatever, but then how you are accessing the internet, what happens? So I mean, like Imbal said, there is a concept of network address translation, how that come in play. So we'll discuss about this. Okay, that what is public and private. All right. Okay, so I think determining this is a lot. Not now. 1 second. But I mean, any